Hello, we are Group 24 working on visual inspection automation. Our names are Junyan Lee, Emily Macheski, James Liebler, and Timothy Goodwin. Jonal Laboratories Incorporated is a custom manufacturing company that primarily produces elastomeric components for the aerospace industry. Currently, Jonal uses a team of quality inspectors to manually examine each part for defects, including chips, contaminations, flashes, and more. However, this is a tedious, non-value-added process subject to human error. Introducing automation would remove pressure from the inspectors, provide them more time to focus on value-added tasks, and increase the speed and efficiency of the defect detection process. Thus, this project entails creating such an automated system to classify a part image as either defective or not defective. The core of this project is analyzing an image and performing a binary classification on this input, requiring the use of deep learning techniques. General machine learning requires the programmer to manually choose a feature selection process to be used to train the classification model. Deep learning is a sub-branch of machine learning that uses successive layers of increasingly meaningful representations and automates the feature extraction process.
Convolutional neural networks are one of the most commonly used tools for image recognition. Neural networks take in information in the form of RGB values, numbers, and use these observations to learn over time. CogNets use the convolution operation, a mathematical operation on two functions that produces a third function expressing how the shape of one is modified by the other. These algorithms begin by taking in the image and progressively learning larger and larger features within the image. It does this for each training image that it encounters. As a result, the algorithm gets better at identifying things it has seen before, picking out common elements and learning as it goes. The final result is an algorithm which can perform image classification, being able to tell what is being shown in a given image, provided that the model has been trained to recognize what it has been searching for. The convolutional layers learn local patterns found in the image and build off another as you go deeper into the network. First learning what an edge or a line is, and then learning how these lines connect to form small image components, and eventually learning to make full classifications. At the end of every CogNet, a small subset of layers is dedicated to a densely connected classifier network which performs the actual classification. In order to train a CogNet, training data is necessary. To this end, we work with Jonal representatives to facilitate the acquisition of images of both accepted and defected parts. As these parts became available to Jonal, they took photographs against a solid, consistent background with consistent zoom, lighting, clarity, and lack of shadows. The images needed to consist of a variety of angles so the model can gain a comprehensive idea of the parts. Since the defects are so small, the photographer must ensure that the defect is visible.
ConvNets for image analysis benefit from the largest dataset possible. However, in real-world applications, this is not feasible, thus necessitating various techniques to accommodate the smaller dataset size. Some of these techniques include data augmentation, dropout, extracting features from a pre-trained ConvNet, and freezing certain layers and retraining a pre-existing convolutional base. For Jonal's specific purpose, the most effective techniques are a combination of data augmentation, which slightly alters existing images to create new images and increase the size of the training set, and dropout, a regularization technique that removes certain units within the data to avoid overfitting. Experiments testing different resolution values were also run, revealing that an image resolution of 900 by 900 resulted in the highest possible accuracy, while still keeping the training process computationally tractable.
Our group trained two binary classification models for two different types of part defects, contamination and chips. The contamination model achieved a 99.2% accuracy, and the chip model achieved a 98.23% accuracy. These high accuracy models provide a proof of concept that convolutional neural networks can be used to automate the inspection process for manufacturing companies like Jonal Laboratories. As a final deliverable for Jonal, we are providing a software package which abstracts out the training, tuning, and evaluation of the convolutional models so they may expand on the current models and train new models as more training data is acquired. Thank you to everyone at Jonal Laboratories, especially the quality director, Ed Hernandez, who acted as our primary point of contact, and our advisor, Dr. Weiwei, for his expertise and guidance.